My name is Luke Choi. I'm a senior at Avon High School, and today I'll be talking about how we can use centroids and homothety to solve selected problems from the AMC 12. So first, what is a centroid? Well, in a triangle, a segment is called a median if it connects one of the vertices of the triangle and the midpoint of the opposite side. And it turns out that when you draw the medians from all three vertices, which is shown in red here, these lines actually all go through the same point, and we call this point the centroid, commonly denoted as G. And the centroid has many nice properties, but the one we'll be using today is the fact that the centroid splits the median into a 2-to-1 ratio. So this also means that this is in a 2-to-1 ratio, and this is also in a 2-to-1 ratio. And as an immediate corollary of this, we have that the ratio between the distance between the vertex and the centroid to the entire length of the median is actually in ratio 2 to 3. Because obviously, if we set AG to be 2x, we know that G splits the median into ratio 2 to 1, so this must be x. So AG to the entire median must be 2x over 2x plus x, or 2 to 3. And we'll be combining this with a technique called homothety. In homothety, you have a figure, in this example ABC, and a center, O. And a homothety centered at O is essentially a dilation. So as you can see here, if we dilate ABC with respect to center O, then we'll get the resulting triangle A1, B1, C1. And there are a few things to note from this. First, we know that since it's a dilation, we are preserving similarity. So triangle ABC is similar to A1, B1, C1. Furthermore, we also know that OA to OA to OA1, the ratio of these two lengths is equal to the ratio between OB to OB1, and also OC to OC1. And you might be able to see how we can connect the centroid and homothety right now, but we'll go into a few examples to see them in action. So the first problem is problem 13 from the 2018 AMC 12B, and essentially the problem gives you a square of side length 30 and a point P inside. And given some lengths, they want us to find the area of the quadrilateral formed by the centroids of these four triangles. So essentially, the quadrilateral formed by these green vertices. So at first, there's not much to go with because the centroids are kind of floating in space and aren't really on any lines. So it's very difficult to work with, especially since we're trying to find an area. So the idea here is that we can actually, quote unquote, push these green vertices to side lengths of the square and get a figure that has an area that's much easier to compute than this green quadrilateral. And in fact, this will be a homothety centered at P. So say we take a homothety at P of ratio 3/2. Well, from before, we know that this will send the centroid of a triangle to the midpoint. Since P to this, sorry, I'm still in laser mode. Since the ratio of P to the green point to P to the yellow point is 2/3, and since we're going from a smaller figure to a larger one, we must invert the ratio, and that gives us a scale ratio of 3/2. Similarly, if we take the homothety at P with scale factor 3/2, this will send this green point to the midpoint of DC, this to the midpoint of BC, and this to the midpoint of AB. And because homothety is a dilation, we are guaranteed that the quadrilateral formed by these yellow vertices is similar to the quadrilateral formed by the green vertices. So what that means is once we find the area of the quadrilateral in yellow, then because we also know the scale factor, we can scale down the area accordingly to find the area of the green figure. And it turns out that the area of this yellow quadrilateral is really easy to find because that on the green points are the centroids, we know that these are all midpoints. Well, the quadrilateral formed by the midpoints in a square simply has half the area of the square. And this is not very hard to see. So the area of this the yellow quadrilateral must be exactly half of the big square, and which has area 30 squared. So that means the area of the yellow quadrilateral is exactly 450. Then, since we're now going from larger to smaller, we must inverse this ratio once again, and we must go down 2/3. So the area of this green quadrilateral, since area ratios square length ratios, must be exactly 2/3 squared of the yellow quadrilateral, or this is equal to 4/9 times 450, which is equal to 200. And looking at the answer choices, that is indeed an answer. So this is the correct answer. So taking a step back and going through what we did is we first saw the 4 centroids and noticed that they were quite difficult to work with because they're just kind of floating there. And what we did was take a homothety at P and use a scale ratio and to send these 4 centroids to the midpoints of their respective sides. And because we know that centroids split medians into a ratio 2:1, we can easily derive that this homothety scale ratio, this dilation factor, must be 3/2. And this gave us a shape whose area is much easier to compute. And once we found that area, we could just scale back down with area ratios. And this is going to be a common theme in problems that have centroids. Not just one, but usually several centroids are usually going to involve some sort of homothety centered at a common point. So this next problem is problem 25 from the 2019 12B, and we won't be going through the entire problem, but we'll use this centroid homothety trick to get the key observation. So in this problem, we are given a quadrilateral ABCD. We're given the lengths of BC and CD, and also we're given that the triangle formed by the centroids, a triangle ABC, BCD, and ACD, form an equilateral triangle. So G1, G2, G3 is an equilateral triangle. And they want us to maximize the area of ABCD. Well, the first step is to decipher what this equilateral triangle condition means. Again, we have floating centroids, so we want to choose a point so that we can take a homothety to send these 3 centroids to the midpoints of the respective sides. And what we can notice is that triangles ABC, BCD, and ACD all have point C in common. So that motivates us to actually take our homothety at C. So again, if we take a homothety centered at C with scale factor 3/2, this will send on G1 to the midpoint of AB. This will also send G2 to the midpoint of BD and G3 to the midpoint of AD. So because it's a homothety, the triangle formed by the yellow vertices is similar to G1, G2, G3. But since all 3 of these yellow vertices are midpoints of the sides, this yellow triangle must actually just be the medial triangle of triangle ABD. And it's easy to see. It's well known that this triangle is actually similar to ABD. So because G1, G2, G3 is similar to the yellow triangle, and the yellow triangle is similar to ABD, by transitivity, this means that G1, G2, G3 is similar to ABD, and because we are given that G1, G2, G3 is an equilateral triangle, that must mean that ABD is also an equilateral triangle. So now we've reduced the problem to, given a quadrilateral ABCD, ABD is an equilateral triangle, and lengths BC and CD maximize the area of ABCD. And while we won't go finish this problem, it's easy to do this with some trigonometry. But again, the key takeaway here is that whenever we have multiple centroids, like in these two problems, the idea is to find a suitable center, C, so that we can use a homothety to send them to the midpoints and make the problem an easier version of itself.